Okay, so far we have been looking at the free particle. Well, let's put particle in parentheses, because what we realized is that when we try to model a relativistic particle, we found that we really ended up with a field. So it's the free field that we've been looking at, and we really are moving towards forces on the particle or the field. So that really sort of, and instead of talking about forces, we really should be talking about interactions, because it's no longer a particle concept, it's a field concept. So we have interacting fields. This will be similar to what we did in regular quantum physics, where we had a potential v of x in one dimension. We'll add a potential in the energy term, and of course that affects the Lagrangian. We've already seen this in the real scalar field video that we recently did. And what we really want to do here is get some intuition about the math that we will need in order to be able to solve these the equations of motion, or rather the solutions to the equations of motion with potentials. In other words, interacting fields. And so to do this, let's go to electromagnetism, because the formalism will be the same. And so let's write one of Maxwell's equations. The divergence of the electric field is equal to charge density over epsilon naught. So we know that the electric field is minus the gradient of the electric potential, and therefore we can say that minus del times, I just pull the minus sign out, this equation becomes, looks like that, and therefore we get del squared of the electric potential is equal to minus the charge density over epsilon naught. So now let's imagine that we have a point particle. So we know how to treat this, right? So if the charge density is, so now it's a point particle, so really it ends up being a delta function. So we have some constant to make this the right units, but delta, so we're in three-dimensional space, so we put a particle at r equals r naught, and the charge density therefore vanishes everywhere except at that one location, and we need it to be a delta function because under integration we need a finite quantity. So, right, the total charge in the universe in this case for one particle is just, well, it's always the charge density integrated over the entire volume, right? And that in this case is C delta R minus R naught in dV, and of course the delta function singles out R naught, and it just gives you the value C. So we have that, and it's a finite total amount of charge, and so that's the correct description for the charge density. And so what is this equation? What does it look like for a point particle? Well, it's del squared, let's say phi 1, because we only have one particle. So let's call it phi 1, and that ends up being minus C times this delta function over epsilon naught. Now, notice that we know that del of 1 over r is equal to minus r hat over r squared, and that's just proportional to the electric field, because we know the electric field of a point particle is just charge r hat over 4 pi epsilon naught r squared. So it goes like r hat over r squared. And so this is telling us that phi 1 is just this kind of thing, right? Because we get the electric field by doing the gradient of the potential. And so phi 1 must be, specifically minus c over, epsilon naught, but then the r is really r minus r naught. So it looks like that. So let's think of spreading charge out continuously, or making it a collection of point particles. So we can talk about phi electric, right, in terms of things like phi 1. So the electric potential is the integral of these kinds of things. We're talking about a linear solution, so we're just adding the potentials of all point particles. So this becomes minus c right. We need the number density. So we're integrating. This tells us where the charged particles are in space, and so really we're integrating over r naught, right? R naught has different values where all the particles are, and we can sort of spread them out continuously. And so c times rho n is really the charge density. And we get another sheet. And so phi of r is equal to minus c rho n dv. We're just integrating over point particles. They're spread out all over space. So it looks like that, minus rho e dv. Like that. And so we can sort of summarize what we've just learned, which is that we have del squared phi for this electric potential. This is the equation it obeys. We have some charge density. And if we can solve an equation that involves only one source of electric field or of electric potential, and so we end up with this. We have a delta function in there. Then, so if this, then we can get the overall electric potential by integrating over all point sources. So it's this kind of thing. Well, apart from a constant, it's phi 1 over. Okay, so the solution is the integral over all point sources. So let's just write that. The solution is the integral over all point sources. That's here. And the same thing will be true in quantum field theory. We'll have an equation, we'll have a free particle, then we'll put a source, and if we can figure out what the solution is to a point source located at one location in space-time, then we can easily figure out what it will be. It's the same kind of formalism.